I'm Daman Panesar from the University of Toronto. I would like to start by expressing my gratitude to the organizing committee for inviting me to participate in this very special 75th Rilem anniversary event. I will be speaking about concrete durability performance from materials to structures. There are several considerations that warrant attention when trying to extrapolate knowledge, concepts, and mechanisms associated with concrete material durability to existing reinforced concrete structural elements. Some of those are presented here on the slide. I will specifically be speaking about the effects of reinforcement on ASR-affected structures, particularly the effect of reinforcement on the ability to confine, restrain, and stress the response of concrete to ASR. This work has formed the basis of student dissertations and manuscripts, and throughout the presentation, when I present the references on the upcoming slides, it is the students' names who are presented in bold. Some initial experimental parameters that are set, which apply for the various studies that I will be presenting in today's talk, is that the reactive aggregate is a coarse aggregate sprat, which is a siliceous limestone. All of the specimens were cured in an accelerated ASR chamber at a 50 degrees Celsius temperature and a greater than 98% relative humidity. And we were also cognizant of the sensitivity of the specimen shape and geometry to the anisotropic behavior of the measurements. And so wherever and whenever possible, we tried to take triaxial measurements, including assessing the volumetric expansion. This slide shows a typical concrete mix design that we used in our study: high alkali GU cement, again, reactive coarse aggregate, non-reactive sand, and the concrete was boosted with alkali pellets. To evaluate the confinement aspect, we conducted the pull-out test on about 72 different specimens using an MTS universal testing machine operated in displacement control mode. The bar displacement relative to the surface layer of concrete was measured using 3 LVDTs, as you can see here in the schematic, and the slip was measured up to 12 to 14 millimeters, at which point the instrumentation was removed and the bar was completely pulled out. Other than the concrete variable of reactive and non-reactive aggregate, we did pull-out tests at 3 different ages: 23 days, 4.5 months, and 7 months, to try to see the progression of ASR, the relationship between the progression of ASR on the pull-out test results. We also had 4 reinforcement configurations: no reinforcement, transverse only, so a number 3 spiral with 100 millimeter pitch, longitudinal reinforcement only. We had 3 10M bars located 120 degrees from each other. And the LNTR case is simply the superimposed effect of the longitudinal reinforcement plus the transverse reinforcement. And the bonded length for all of the specimens was 100 millimeters. And the pull-out bar itself was a 20M steel bar. This figure shows the bond slip response at 7 months for the 4 various reinforcement scenarios. So just to highlight a couple of the main points, first let's look at the plain concrete, the non-reinforced concrete. So what we can see here, the black lines are regular concrete, the red lines are ASR concrete. And what we can see here is that there is a reduced bond strength of ASR concrete in comparison with the control concrete, and that's reflected by those 2 blue arrows. In contrast, if we compare that to the most heavily reinforced samples that we examine, the TRLN case, we see that the ASR response of the stress slip relationship is quite different. The bond stress actually plateaus for a longer distance, up to a slip of about 4 millimeters, due to the triaxially reinforced specimen and the added confinement response. In terms of the failure modes that were observed, most of the specimens observed a fairly classical pull-out failure. The only ones that didn't were the longitudinally reinforced specimens. And here we can see in the stress slip curves there is a sudden loss of load carrying capacity at about 7 millimeters load end slip. And this corresponds to the visual observation of cracks extending from the steel concrete interface to the outer surface. And these cracks are visually apparent through the entire length of the specimen as well. So although there was observed that the specimens that had a transverse reinforcement alone or in combination with the longitudinal reinforcement had some benefits with respect to bond capacity, and that most of the specimens we looked at did have a pull-out failure mode, we should note that these experiments were only done up to 7 months. And so more severe ASR expansions would have to be studied to get a better, more comprehensive understanding of the evolution of ASR on the steel bond strength. So moving to the effect of reinforcement on the ability to offset response to ASR. Again, here we also looked at triaxial reinforcement by use of steel fibers and longitudinal reinforcing bars. We had 5 different reinforcing scenarios in this case. The Dramix RC8030 steel fiber with 3 different volume fractions, 0%, 0.65%, and 1.3%. And some of these fiber reinforced concrete mixes, the prisms also had a central reinforcing bar, a 6.4 millimeter diameter bar, which corresponds to a 0.365% reinforcement ratio. So some of them had the bar and some didn't. What we measured was 4 different expansion measurements, 2 longitudinal measurements of the core of the prism, as well as the surface, and 2 transverse expansion measurements, one perpendicular to the direction of casting and the other parallel to the direction of casting. And the transverse expansion is represented as the average of the perpendicular to parallel to casting. So first, to look at the longitudinal expansion, specifically the core to surface longitudinal expansion ratio that is presented on the vertical axis here, and the horizontal axis is the age. So what we see is the expansion is very sensitive to the presence of rebar as well as the positioning of the measurement. And so without specimens, the prisms without the reinforcing steel, that central bar, irrespective of the percentage of fibers, the core had a greater expansion than the surface, up to 25%. In contrast, the specimens that did have this central longitudinal reinforcing bar, again, irrespective of whether or not there was steel fibers, the core had a reduced expansion compared to the surface by up to 25% also. And so interestingly, the expansion gradient from the core to the surface becomes reversed depending on whether rebar is present in the specimen or not. Now, to look at the comparison between longitudinal and transverse expansion, so the vertical axis on all these 4 plots is the same. The bottom 2 are transverse, the top 2 are longitudinal expansions. And so basically, this is what we have seen even for unreinforced prisms, that whereby the transverse expansion is in many cases markedly greater than that of the longitudinal expansion. And this is attributed to the size effect, casting direction, geometry, etc. But further to this observation, what we found is that the role of reinforcement as rebar or by fibers appears to be quite interesting. For the longitudinal expansion, the presence of rebar or increasing presence of fibers reduces the longitudinal expansion. However, there seems to be a phenomenon of that expansion transfer to another direction, because when we look at the transverse expansions, the presence of rebar results in some cases an increase in the transverse expansion. And also the bottom right slide figure here shows that increasing the percentage of fibers actually increases the transverse expansion. So to take a closer look at that transverse plane, we conducted the damage rating index on that YZ surface where we evaluated 7 petrographic features. I'm not going to get into too much detail about the index itself, but I will highlight some of the features that were observed, which show the potential roles that the fibers was playing. So we see that the crack is branched by a fiber. We also observed that fibers did provide some confining effect. So there was less paste cracking compared to the 0% fiber case, as well as less dispersion of gel into the paste matrix. And we also observed the accumulation of ASR product around the fibers. And so looking closer at that interfacial zone and the bond between the fibers and the matrix would also be some necessary next steps to understand the mechanism. So although we did find some benefits with the fibers, which in terms of reducing paste cracking, partially or completely offsetting loss of mechanical properties such as elastic modulus and modulus of rupture, part of the complexity in understanding the real role of the fibers and the reinforcement was affected by the anisotropic behavior due to the geometry. And so, and specifically meaning that, you know, fibers and the reinforcing steel seem to reduce the longitudinal expansion, but there was a transfer mechanism into the transverse, reduce the longitudinal expansion, but not necessarily the transverse direction. Sorry about that. So in our next study, to try to eliminate the effect of the geometry complications, we looked at cube specimens, specifically to look at expansion stress relationships. We developed a method to apply and sustain multiaxial compressive stresses within the concrete, and this approach was conducted using a post-tensioning method of pre-stressing high-strength bolts. We considered 7 different stress states, and those are shown here on the slide. Non-stress case, 2 scenarios of uniaxial loading, 2 scenarios of biaxial, and 3 scenarios of triaxial loading. Our 29 cube specimens were 254 millimeters in dimension. And this figure shows some of the results. So here we have the vertical axis is expansion. The horizontal axis is the first set of data is the non-stress case, the X, Y, and Z direction. And here we see, as we would expect, very similar expansion measurements. For the 2 biaxial cases, low load and high load, we see that in the loaded directions, X and Y, there is some suppression of the measurement in the X and Y direction. So that's the red and blue bars. But then we see in the free direction, the yellow bar, there is a transfer of that expansion. Also shown here is the volumetric expansion, these 3 black dots. So irrespective of the large difference between the stressed axes and the unstressed axes, the volumetric expansion seems to conserve itself. Further to that, this shows the volumetric expansion for all of the stress states, and we can see that all, with the exception of the triaxial case, had a very narrow band of ultimate volumetric expansions, and it was the triaxial loaded scenarios that did have a marked reduction up to about 70% reduction in volumetric expansion. The ability for other approaches to be sensitive in this phenomenon of suppression and transfer we did the damage rating index on 3 different planes for each of the stress states. And so this analysis also captured and was sensitive to higher damage for free directions, lower damage for the stress axes, and in general, for triaxial case, similar damage rating index for each of the 3 planes. Anisotropic behavior was also confirmed by coring these cubes, and we can see that for the biaxial case in the free direction, there was a loss in modulus of elasticity compared to the stressed direction. And so I'm not going to get into too much detail about what the conclusions here. I will, however, summarize the various concepts and aspects that we have studied. So related to bond strength, reinforcement and restraint, and multiaxial compressive strength. We continue to investigate these aspects with different scenarios, with different aggregates. We believe there is a need for that to be able to link better concrete material degradation mechanisms to actual field performance, particularly because the impact of the outcomes are quite important, both from a modeling perspective and from a field perspective. So for modeling, advancing numerical and analytical models to capture multiaxial expansion stress relationships is necessary to refine estimates or predictions related to long-term performance of ASR affected structures. And from a field perspective, designing destructive and non-destructive testing and proper interpretation of the role and proximity and direction of the reinforcement relative to coring and sample retrieving is critical in order to make appropriate assessments of condition assessment data. With that, I would like to acknowledge again the students who have really been very passionate about this work, as well as sponsors of this research. These are the references that were cited throughout this presentation. And I would like to thank you for your attention, and I'm happy to take any questions.